And at this point, like, you guys aren't going to show up in the recording because of the way that I have the recording set up. Like, you won't show up, like your faces or whatever. So don't worry about that if that's the kind of thing that, like, excuse me, it concerns you at all. Okay, so first order of business, we're going to talk about, or actually, we're going to take a look at something that's really cool. So our first reaction of the day is actually magnesium combustion. So let me show you. Yeah, let me open up my Chrome window. Okay, this will do. And then I'm actually going to go here, and then I want to go here. There we go, this one. Okay, so check this out. So this is a really fun reaction that I love to do during the year. It's cool for, like, studying ionic compounds or studying combustion or any other number of things. But let's take a look at what's happening here.
This is magnesium ribbon, 75 feet of it. This is actually fairly cheap. It's $5 on Amazon.com. And this can be used for starting campfires because magnesium, there's not much that can put that out. It'll even burn wet. I tried using a lighter to light a small piece of it. It actually takes a little bit of time. The fastest way to do it is to get a blowtorch on it. But for camping purposes, it's better to buy chips or powder of it because that'll light up faster. So I'm going to take a small portion of this. All you got to do is bend it like this, really tight, like fold it, and it will automatically snap. Stuff burns very hot and bright. You shouldn't look directly at it while it's burning. It's very bright. I'm going to put it on top of bricks so it doesn't melt the asphalt. And I got a blowtorch here.
So what's really cool about this reaction is that you normally don't think about metal as something that burns, right? Like, you think about metal as it's something that gets hot or maybe melts, but burns. But here we go.
There it goes. Burns very bright. It makes some smoke, but it doesn't burn for long because this isn't a big piece. You can actually buy bricks of it online. Those bricks, you can shave them, you can burn them as is, but if you like the whole brick, it'll probably melt the hole right through whatever you put it on. Unless you put it on a rock, it may crack it. As you can see, it not much. The ashes you can now blow away. I'm going to try a little
So
bit.
that white stuff there that he calls ash, that's actually magnesium oxide. And so what's happening is the magnesium metal is combining with oxygen in the air to form magnesium oxide. And this is a violent reaction that produces light and heat. So we'll watch one more time. He's going to use a little more magnesium.
Bit bigger of a piece to show you on the video. Okay, here is 18 inches. That is the most of it I'm going to do now. I'm going to ball it up. So like a ball of it. Put it down. Get the torch. Go. That flame's going to get much bigger than the last one. It makes some smoke. I don't know if that's toxic, so I'm not going to go in it.
Yeah, that's
See, it's twinkling.
vaporized magnesium
sparks.
oxide. You don't want to breathe that.
Very bright to look at. So I'm looking at it on the screen. That helps a lot. It's not going to burn for long. It'll be out in a few seconds. This is a good product, especially for starting fires. I'll make another video of this. What happens when you pour water on it. As you can see, it's not burning anymore. It's just super hot. That's what you're seeing now. It's very red. Actually, on the screen, you can't see it. It looks white. That's just ash.
Okay, so that's a really cool demo, and we can actually do that in the lab. I don't have any magnesium on me right now, but it's the kind of thing we can do. So welcome back, Kyra. So I'm going to share my whiteboard. And so this is what was going on there. So that was magnesium combustion. So we saw magnesium combustion. Okay, magnesium combustion. And here's what was happening. So, and scholars, by the way, if you're confused during any portion of this, what I encourage you to do is go ahead and chat with Ms. Alcaraz and let her know what your specific questions are, okay? And she'll be able to answer them, or if you ask something that's sort of beyond the scope of what we've discussed, she'll let me know so that I can answer that question, okay? So please go ahead and just shoot her a text or shoot her a direct message in the chat window if you have any issues, okay? And so now I'm just going to move back. Okay, so we're talking about magnesium combustion today. And there we go. And magnesium combustion works like this. So that should be a capital M. Magnesium plus oxygen gas yields magnesium oxide. Okay, and this is clearly a combustion reaction. Who can tell us what the big giveaway is that this is a combustion reaction, besides the fact that you saw, you know, the demo with magnesium burning and producing light and heat? What's the big chemical indicator here that this is a combustion reaction?
O2, right?
O2, Ryle, very good. So remember, combustion means combination with oxygen, right? And there should be some light and some heat produced. It needs to be a violent combination, not just a slow combination, okay? So when rust forms on your car, indeed, the iron is reacting with oxygen, but that's not a combustion reaction. There's no fire involved, okay? So we've got this reaction, and we want to ask ourselves whether it's balanced. All right, so Andrew Ledesma, how many oxygens are on the left side of this equation, of this reaction arrow?
Hey, hello, can you hear me?
Yeah, I can. How many oxygens are there, Andrew?
One.
Well, one
Two,
oxygen
sorry,
molecule,
two.
but how many oxygen atoms? Good, 2 oxygen atoms, right? So 2 oxygen atoms. How many oxygen atoms are on the right side of the arrow?
One.
1. So that situation's not balanced. Andrew, do you know what we do to balance that particular situation, to balance the oxygens at this point?
Put a 2
Where?
in front of the M.
Good. So you actually put a 2 right here. And here I'm going to highlight in red something that you cannot do. What you cannot do is put a 2 here. If you put a 2 right there, then you're actually changing the chemical. That would be magnesium dioxide. That's no good, okay? That doesn't exist. So we get rid of that. This is magnesium oxide. We have 2 copies of magnesium oxide, okay? Those are called formula units because magnesium oxide is an ionic compound. So 2 formula units of magnesium oxide, okay? So now we have 2 oxygens on the right and we have 2 oxygens on the left. So 2 times 1 oxygen here, that means 2 oxygens, and then O2, so 2 oxygens here. Okay, the oxygens are balanced. But Kyra, what's going on with the magnesium? Is the magnesium balanced? How many magnesiums do we have on the right?
2.
2 magnesium atoms on the right. What about on the left side?
1.
1. Okay, so those are not balanced. So Kyra, can you tell us what we would do to balance the magnesium atoms? What would we do to balance those magnesium atoms?
Add a 2
Add a 2 where?
in front of the M.
Good. So on the left side, we add a 2 in front of the magnesium. And then we can see very clearly, right? So we can see that that for magnesium and for oxygen, right, on the left and on the right, okay, make a little table, right? We've got 2 magnesiums on the left and 2 magnesiums on the right. We've got 2 oxygens on the left and 2 oxygens on the right, okay? And that tells us that our equation is balanced. In balanced chemical equations, we have to have the same number of each type of atom on each side of the reaction arrow. And the reason for that is that during chemical reactions, atoms are neither consumed nor produced, okay? So what I'm gonna do is erase this. So take a screenshot if you need to right now, and this lecture video will be up. And I'm going to put those 2 definitions on the board shortly. So I'm gonna give you 3 more seconds to continue writing down. If you're struggling with that, just take a quick screenshot, okay? But I'm gonna erase this board in 3, 2, 1, okay. So here are a couple important definitions, okay? So during chemical reactions, atoms are neither created nor destroyed. Okay, and a little moment for thinking about chemists and scientists as writers, right? We have to understand common expressions and language constructs. So we have to know things like the fact that neither and nor go together. Okay, so atoms are neither created, right, nor destroyed. So those are important things for us to know as chemists, how our language works and how to communicate effectively. So another important corollary of this is that the same number or count of each type of atom should be present on, I'll write a better T, on both sides of the reaction arrow for a balanced chemical. Okay, equation. Okay, so for a balanced chemical equation, you have to have the same number of each type of atom on both sides of the reaction arrow. Okay, very, very important. Otherwise, your equation's not balanced. And so we don't write equations that way because we're proper chemists. Okay, so take a few more minutes to write this down. In the meantime, I want to take any questions that we might have. So who can share a question with us, or who has a question for me?
I have a question. It says should be
Present,
present.
yeah, or shown. A better word actually is shown. I'll change that, but present also works. Shown or okay. So may I erase the board, or do we need a few more seconds?
You could erase the board.
Okay, everybody cool with the board being erased? All right, so take a screenshot if you need one. Otherwise, it's gone in 3, 2, 1. Peace out, board. Okay. So I want to show you something else that's really, really cool. So we talked about magnesium combustion. I also want to show you another really cool reaction, which is hydrogen combustion. So we'll go to hydrogen combustion. Yeah, hydrogen combustion. And there was this really cool one right here. This guy does a great job.
So let's take a look.
Okay, boom, boom, and let me share this screen. So share screen, go here, right here. Okay. So this professor does an awesome job. Like I couldn't explain this any better because he just crushes this. So here we go.
So let's take a look at the reaction of hydrogen and oxygen. My hearing is bad enough, so I'm going to put these on, just so I don't have to hold my fingers in my ear. There's a seal to keep the hydrogen in. And it's actually, I filled it from the bottom, so there's a little opening on the bottom. I'm going to take that off. And now, on the top here, I have an opening. If I light this, let's light this baby. What happened? What do you think was going to happen? What do you think was going to happen? Well, you've seen the hydrogen-oxygen reaction before. But remember that in order for hydrogen and oxygen to react together, we got to have both hydrogen and oxygen. If I have a can filled with hydrogen without oxygen, we can't have a reaction. I only get a reaction where the hydrogen escapes from the can. So, what just happened? What just happened? Well, as the hydrogen was escaping out the top of the can, what was going in the bottom to replace it? Well, air, and that air contains oxygen. So as the concentration of hydrogen in the can was going down, the concentration of oxygen in the can was going up, and eventually we reached a point called the explosion limit. And when the ratio of hydrogen to oxygen got to a certain point, then the reaction between them occurred very rapidly, and we got the familiar combustion, the familiar explosion reaction. All right, so you just got your first lesson. The reaction rate, or the rate of a chemical reaction, is going to be dependent on the concentrations of the reactants. I only get a reaction where the hydrogen escapes from the
Yeah, that dude's the boss. Okay, so really enjoyed his presentation there. So let's talk about that reaction. So where is, there we go. Okay. All right, so what in the world happened, right? So that was hydrogen combustion. And here's what we have in hydrogen combustion. We have H2 plus O2 yields H2O. Okay. So what happened in that reaction, right? So at the beginning, there was hydrogen inside the can, just hydrogen. And it was burning because it was combining with oxygen in the room, okay? But as that hydrogen's concentration depleted inside of the can, the oxygen concentration inside of the can increased. And once we got to the right level, these two were able to combine directly and very efficiently inside the can, all at once, right? The air that was going into the can had oxygen inside of it, right? And that oxygen reacted violently with the hydrogen, okay? And boom, we got our big explosion. That was really fun to watch. So that produces water, just water, okay? That's it. So what it does not produce, it does absolutely not produce H2O2, okay? That's hydrogen peroxide. So if you wanted to balance this equation, you might be tempted to write a 2 there, except that would not be okay, okay? We cannot write a 2 there. So we've got to adjust coefficients, all right? We've got to put some different numbers out here or over here, right? You've got to figure, we've got to figure that out, okay? And so what I want you to do is take the next 2 minutes to try to balance this equation yourself, okay? So I'm gonna set my timer, give this a shot for the next 2 minutes, and if you have questions, just hold on to them, okay? Because we'll balance it as a class afterward, but I wanna see who can do this, all right? So on your own, try to balance the combustion for hydrogen in 2 minutes. Go ahead. Hey Siri, set timer for 2 minutes.
Okay, 2 minutes and counting.
Okay, so here we are. All right, Ronald, are you there? Are you trying? You working? Okay. Okay, so here's our chemical equation. Who wants to take a stab at this? Who wants to give this a shot? Who thinks that he or she might have the right answer?
I think I got it.
Okay, Robin? Okay, Robin, why don't you get us started, okay? So what's the first thing that you see that's not balanced?
The or the oxygens.
Yeah, we have how many on the left?
So, 2 and then 1 on the right.
Yeah, 2 on the left, 1 on the right. So that's not going to do the trick. Okay, so what do you have to do here?
I added 2 in front of the O on the right side.
What, like here?
Yeah.
No, we can't do that, right? Because
Oh, I mean on the whole
one
equation.
chemical. This is one chemical, right?
Yeah. I added it in front of the H.
Okay, got it.
Yeah.
Okay, so that I'm going to stop you there. Okay, very good. So now our oxygens are balanced. Okay, but who can take over from this point? Who can get us all finished? So now our oxygens are balanced, but what's not balanced? And who can finish this equation?
What I did was I put a 2 in front of the H on the left side.
Who's this?
Andrew Ledesma.
Andrew. Okay. You put a 2 in front of the H on the left side. Okay. Why did you do that, Andrew?
Because the hydrogens on the right side is 4.
Okay. 2 times
it's
2 is
not
4, right? We've got,
Yeah.
hold on a second. We've got 2 copies of the water molecule. And we know that each water molecule has 2 hydrogens. So that means 2 water molecules, well, 4 hydrogens. Okay. 2 times 2 gives 4. And so you're saying over here, we got to have 2 copies. Welcome, Ferlin. We got to have 2 copies of the hydrogen gas molecule. Okay, so how many hydrogens on the left now?
4.
Okay, so is our equation balanced?
Yes.
Okay. All right, let's see. Okay, so on the left, we have 4 hydrogens, and on the right, we have 4 hydrogens. On the left, we have 2 oxygens, and on the right, we have 2 oxygens. Okay, so that's a nice little handy way for us to check how many oxygens and hydrogens we have on each side. Okay, if this table is the same on the left and the right, we know we're good. Okay, so that was a fun reaction. Here's another reaction that's going to do a good job. So may I clear this, or are we still copying down?
We're still copying.
Okay, Hannah, did you get all this copied down? I feel like you're doing something else.
Good.
You're good? You got all this?
Okay, it's good.
All right, so I'm gonna go ahead and erase this screen. 3, if you need a screenshot, take a screenshot, but otherwise I'm erasing in 3, 2, 1, okay. And so we're gonna look at a different reaction now. So we're gonna look at aluminum plus hydrochloric acid yielding aluminum chloride plus hydrogen gas. Okay, that's H2. Let me draw a slightly better 2 there. H2. Okay, man, I'm just gonna do this again. So Al plus HCl, okay, yields AlCl3 plus H2. Okay, that's clear. All right, so the first thing I want you to do is figure out what type of reaction this is. Okay, don't say so out loud if you know, but figure out what type of reaction that is. And then I also want you to balance the chemical equation. Okay, so let's give that a shot. Okay, so take the next 3 minutes, look through your notes, figure out what type it is, and then let's balance that bad boy. Okay, so 3 minutes, go for it. Hey Siri, set timer for 3 minutes.
Your timer is set for 3 minutes.
Okay, and if you have questions, now's a really good time to send Ms. Alcaraz or me a private message to let us know what your questions are. Okay, if like this is confusing you, etc., whatever it is, go ahead and message us. Okay, Scholar, so that's time. So does someone feel like, so let's talk first off about what type of reaction this is, okay? Who can get us started on what type of reaction we've got here? Welcome back, Ferlin. Good to see you, Ferlin. Okay, so I want to hear from Layla. Layla, do you have a sense of what type of reaction this is?
Single displacement.
Okay, Layla says single displacement. All right, Layla, why did you come up with single displacement?
Because with our definition of single displacement, it's basically one of the, what's it called? One of the chemicals gets separated from the other. I don't know if I'm explaining this right, but like one of them gets
That's what we
separated.
do. Like welcome to my world. We have to explain what's going on. It's okay. It's not easy.
Yeah.
Go ahead. So try what happens?
Basically, one of the chemicals gets separated from the bunch. Yeah. I'm sorry.
Okay. So which chemical gets displaced?
The hydrogen.
Okay. So H is displaced by what?
By the chlorine.
The chlorine's displacing the hydrogen? The chlorine takes its place and bonds to itself?
No, the aluminum.
The aluminum. Okay. That's what's happening. Hydrogen is displaced by aluminum. Okay. Right. So look, you had this hydrogen over here bonded to chlorine, and now an aluminum is bonded to chlorine. So the aluminum comes in, and then the hydrogen gets kicked out. Okay. That's what's happening. So there's your classic single displacement reaction. Okay, so I'm going to erase those little arrows that I just drew and those lines I just drew. Okay, and just leave the written explanation. H is displaced by aluminum. So that's what you should be visualizing when you read those words. H is displaced by aluminum, right? Aluminum comes in and kicks the H out. Okay, and then I want to hear from Araceli. Araceli, do you have a sense of how this reaction should be balanced?
Huh?
Have you tried balancing the reaction?
No.
Okay, then let's get started just a little bit. I'll start with you. Can you give me one atom or one element that's not balanced, or one element that is balanced in the chemical reaction as it's currently written?
The CO and the H2.
Okay, so let's start with hydrogen, right? So hydrogen on the left, there's one, and then there are two hydrogens on the right. So is the hydrogen balanced?
I guess.
Well, if there are two on the right, but only one on the left, do we have to, no, right? So it's not balanced. Okay, so that's not a balanced chemical in that equation. Okay, so this one actually looks a little strange, right? So you could try to play around with this. So follow with me. Or in fact, really quickly, did anybody actually go ahead and balance this thing? Is there anybody who feels like he or she has a balanced chemical equation here? No one feels like they have a balanced chemical equation? Okay, so I'll go ahead and get us started. So the first thing you might notice is that the aluminums are balanced. There's one aluminum on the right, there's one on the left. But the hydrogens are not balanced and the chlorines are not balanced. Okay, so what do we do about this? So we've got H2 on the right and we've got HCl on the left. We want to balance the hydrogens and we want to balance the chlorines. Now the thing is, if we multiply the HCl by 2, then we're going to have 2 hydrogens on the left and on the left and then 2 on the right as well. The problem though is that at that point your chlorines would be unbalanced. You'd have 2 chlorines on the left and 3 on the right. That's no good. So it turns out that what you have to do is use a little more effort. So like you can try a 3 here, and then you'd say to yourself, okay, now I got 3 chlorines, right? And 3 chlorines, I'm happy there, but I've got 3 hydrogens, and there's really no way to turn this into 3 hydrogens. So what I could do is I could put, okay, I've got 3 halves of a molecule, but in balanced chemical equations, we actually don't use fractions. Yet, this is still a clue, okay? Because if I were to multiply both sides by 2, I'd get rid of that fraction. And so what I end up doing is, and you'll get comfortable with this math, don't worry if it seems strange to you right now. I'm going to put a 6 there, and I'm going to put a 3 there. Okay, now I've got 6 hydrogens on the left and 6 hydrogens on the right. I've got 3 chlorines here, so to balance the chlorines, because I've got to have 6 of them, I actually put a 2 out in front there. And now I'm in really good shape, because I've got 6 chlorines on both sides, I've got 6 hydrogens on both sides, and to fix the aluminums, I've got 2 on the right, but only 1 on the left. What do I do? Okay, who can finish this equation? What do I do to balance these aluminums?
Kind of the Al aluminum, right? On the
Good.
left.
Good. Is that Robin?
Mm-hmm.
Good. I put a 2 in front of the aluminum. Okay. So now I'm done, right? That's a balanced chemical equation, okay? And so how do we verify this? So we've got left, right, and we've got, so aluminum, chlorine, and hydrogen. On the left we have 2, on the right we have 2 aluminums. On the left we have 6 chlorines, on the right we have 6 chlorines. On the left we have 6 hydrogens, and on the right we have 6 hydrogens, okay? That's a balanced chemical equation. I don't know why that's taking so long to come through on the video. Like, are you guys not seeing what I just wrote in?
No, you can't see nothing.
That's brutal. Why? Oh, you gotta be kidding me. Okay, my Wi-Fi just kicked out my whiteboard. Why did you do this to me? Okay, so I think I'm gonna end up not filling in that table. And so why is this thing not? Kill that Zoom window. And then looks like my Wi-Fi is okay. Let me check if I can like open up a web page. Okay, that's lagging. I don't know why. Yeah, that's lagging. Okay, so my iPad's like not in a good mood right now. Okay, so what we had there were 6 copies of aluminum and 6 copies of chlorine and 6 copies of hydrogen on both sides, as well as 2 copies of aluminum on both sides of that reaction. Okay, so that means that this is a perfect time for us to do 2 things, okay? 1, again, send a private message to Ms. Alcaraz or me if you have a question. And 2, go ahead and upload your notes to today's notes assignment on Google Classroom. So let me go ahead and post that. So right now you should be taking a picture of your notes, okay? So take a picture of your notes, and then I'm gonna get the notes assignment uploaded on Google Classroom because I don't know that I've posted it yet. So Chemistry 1B. Notes, chemical reactions part 2. Okay, no, so not yet. Let me get the assignment up.
What's the name of these notes? What is the title for it?
These are these are chemical reactions part 3. Chemical reactions part 3. So I'm just going to fix this part 3. Okay. And then boom, boom. Okay. And then let's do today. Let's do today. And then chemistry 1B and chemistry 2B. Okay. And that's assigned on Google Classroom now. Okay. And I'll probably have this graded. I'll have this graded by the end of the day. I grade these quickly. So let's see who's turned in what. Okay, so nobody's turned anything in, of course, because I just posted the assignment. So go ahead, guys. It's chemical reactions part 3, and just start turning in pictures of your notes. Okay, it'll be a quick submission. And then after, we're actually going to talk about current events. I feel like this is a good stopping point. We'll do a little bit of a review of equation balancing at the beginning of next class, and then we'll have a quick check-in. And then we'll continue on. Okay, so right now we're doing, so I don't see anybody turning it in, so please turn in your lecture notes, okay, very important. Turn your pictures in now. and we're going to do a bit of current events right now because we've got a lot going on in the world with this coronavirus situation, and so we need to talk about what's actually happening. Okay. So now I'm back in the meeting with my whiteboard. Just making sure that works. Okay, so 2 of us have turned this in, so Araceli and Robin. And I'm actually just gonna grade this right now. So reactions part 3, but that's wrong class.
I turned mine in.
Thanks, Joey. And I'll be checking back and forth. So reactions part 3. So who's turned this in? Okay, perfect. So Joey and Kayla and Kurt and Araceli and Robin and Layla have turned this in. So I'm going to update the first little set of grades here. So Joey, and was it Kayla? Kayla and Kurt and Andrew and Cecia and Araceli and Robin and Layla. Okay. So Joey and Kayla and Kurt and Cecia and Araceli and Layla and Robin. Yeah, what's up?
I'm gonna go use the restroom. I'll be right back.
That's fine. Go ahead.
Okay.
Okay. Joey, Kayla, Kurt, Andrew. Andrew has turned this in. Very good. Miguel, Robin, Hannah, Gabby, Irami, Ronald. Okay, a lot of people are turning this in, right? So Miguel, Irami, Ronald, Gabby. Okay. Who else has turned this thing in? Layla, we got Miguel and Layla, right? Miguel. Yep, and we got Layla, good. Gabby, Ronald, Giovanna. Okay, Giovanna and Giovanna. Okay, guys, about another minute to turn this in. Okay, about 1 more minute.
I already turned it in.
Joanna?
Yeah.
Joanna, it's not showing as turned in because you didn't hit submit, but I see that you actually uploaded it. So remember to upload and hit submit, but I'll count it for you, okay?
I did hit submit.
Okay, then it's just taking some time. Okay, and then Hannah. Very good. And who else? Not Ryle. So we're still waiting on Ryle and Juliana and Elijah and Froylan, okay? Ryle and Juliana and Elijah and Froylan, we're waiting on you guys, okay? So please turn this in really quickly. You've got about 30 seconds. Yeah. Okay. All right, so I haven't received from you guys. I'm gonna go ahead and mark everybody who has not turned this in at a 0 and missing. And just email me by the end of the day if you've turned it in, okay? If you do that, I'll mark it present and on time, okay? So I just want you to get it in by the end of the day here. All right, so, okay, so let's move on to our next thing, which is actually gonna be talking about current events. And so I'm gonna share my screen with you. So I just got a subscription to this really cool magazine, and it's really like a website, an online news provider. Think of it like you would almost a newspaper. It's called The Atlantic. And so I'm going to show you how this coronavirus or pandemic has been spreading within the United States. So this graph here shows that as of March 1st, we only had 15 recorded cases in the United States. But actually, our real number of cases was likely more like 150 at that time, okay? Because that disease had been circulating throughout the United States from people who had traveled here from China for, oh golly, a couple months at that point, okay, maybe 3 months. And once we've gotten the ability to really increase our testing, we've seen that way more people have this coronavirus. So as of the printing of this article, it was 17,000. Now it should be north of 40,000 in the United States. And what's really happening is that the actual number of cases here in red and then with the arrow bars in yellow, is actually way higher than the reported number of cases at any given time. So if we've got 40,000 reported cases, we've actually probably got more like 300 or 400,000 real cases. Okay, so this disease pandemic is spreading pretty rapidly, and that's a real issue. And another issue that I'm highly concerned about, actually, and I'll get into this, is that President Trump is actually interested in like getting us getting our economy rebooted. So like Trump is concerned. Yeah, so the New York Times was reporting on this. So the cool thing, guys, about the Atlantic is that you can have a full year subscription for $25 as a student, and it's a really good magazine that you can read, and like it'll give you all kinds of interesting stuff. Like I just got the teacher discount, so I paid half price too. So I could have paid $25 for the digital. Instead, I wanted the premium, and I paid $50. But I mean, you can buy whatever you want. It's really nice. So New York Times will also give you a few free articles every single month. And so like, here's the thing I'm concerned about. Trump considers reopening the economy over health experts' objections. So he's wondering if we should just all go back to work, right? And the New York Times argues that that's a crazy idea. And actually, so does The Atlantic. Okay, there's a really good article that I can't find at the moment in The Atlantic that argues about this. So that's kind of what's going on right now. And so I'm hoping that the health experts will get President Trump to come to his senses and keep this quarantine or this nationwide lockdown going on for quite a while longer. I think it needs to probably go on for another 8 to 10 weeks. But we'll see what actually happens. So right now, I just want to open up the floor to questions. So who's got a question about the coronavirus or anything related? This is definitely something we should be talking about in science class. And if you don't feel comfortable saying something out loud, you can go ahead and PM. We're going to get out of here at 9:35 either way. So who'd like to get us started?
Have they found like anything like new that could help like cure the coronavirus or not yet?
Maybe. There's this old anti-malaria drug that might be helping. I think it's called like, golly, cytoquine or something like that. Chloroquine. And so let's look at what that actually is. So I got a chat. So who asked the question? How long do I think schools are going to be closed? So, okay, schools, I think we're closed through at least the end of the year. Chloroquine is this drug. Let me see if I can see the molecular formula of it. So you guys know how skeletal structures work, right? So you guys should go ahead and see this thing. So there's the formula, but its formulas aren't helpful. So this is chloroquine, okay? And that's about as big as I can make it on my current screen, but even that's not doing me a lot of good. So there, that's a little bit better. Okay, there's chloroquine. So let me just zoom in. Chloroquine, okay? So you've got these two benzene, or these two aromatic rings here, and then you've got a chlorine right there, and then you've got a nitrogen. So this is an amino group, and then you've got, man, this I don't know what you would call this structure, but that's your chloroquine, and so that might be helping against this thing, helping to treat it. But we don't have a good treatment yet. Like this thing isn't a miracle, and I mean, but it could end up helping. We just don't have enough data on this guy yet. And what we also don't have is a vaccine. So the vaccine's the real game changer that we're all waiting for. Okay, and so I'm trying to find this article that I saw yesterday that was just absolutely fantastic on, oh golly, so where's the latest? Okay, the future Zoom party, like a college Zoom party. Oh my gosh, Trump, stay alive, Joe Biden, do more. Okay. There was this really good article that I read yesterday, and it's like not even up there anymore, and I don't know why. It was written by two different professors. So trying to find out where's the latest stuff. So okay, I'll see if I can find that article just so you'll see what it's called. Any other questions, guys, while I'm looking for this thing? Okay, I think it was this one. This was at least very good. So pediatrics and global health, right? These are the professors, right? And so so yeah, this is what Trump was saying. So it's tempting at this point to say that the cure is worse than the disease, worse than the disease. It isn't. Okay. And so this article right here really helps you understand the scope of this problem and the right way to address it. Okay. Looks like one last question, then we're gonna bounce. How long do you? Okay. So what's with the kids are not okay article? Take a look. Take a look. Take a look on the Atlantic and see what it has to say. But the bottom line is you guys are not likely to suffer grave effects of this, okay? All right, so if you have any further questions, shoot me an email. Otherwise, scholars, you guys have a great day, okay? Everybody have a great day.
Bye.
Bye.
Hi guys.
Bye.
Mr. Dr. J.
Yeah.
Did you see my email?